and hopefully give you some clear takeaways.
That's the plan.
So today, we're tackling something that probably feels, well, really intuitive to you. This idea, does a larger vibration actually contain smaller vibrations, like a guitar note or ripples in a pond? It just feels like big, complex things must be made of simpler bits.
And that intuition, it's powerful, and there's definitely truth to it, but maybe not quite like nesting dolls,
Okay.
Our mission today is to really dig into that. We'll look at the science, classical physics, quantum mechanics, which gets pretty wild, then some speculative ideas, and even how this connects back to really ancient philosophy. It's quite a journey.
Sounds good. So let's get straight to it. You said not like nesting dolls. What's the scientific picture then, roughly?
Well, the basic idea, scientifically, is more about coexistence and addition. Multiple simple vibrations can be in the same place at the same time, and their effects just add up. That's the key. We call it the principle of superposition. It's fundamental.
Superposition. Got it. So, things adding together. Before we dive deeper, maybe we should quickly define our terms, just so we're all on the same page.
Good idea. So a vibration or oscillation, that's just something moving back and forth periodically around some central point. Simple enough.
Like a pendulum swinging.
Exactly. Now, if that vibration travels, propagates through something, air, water, whatever we call it, a wave, and waves have properties. Frequency is how fast it vibrates cycles per second. Think high pitch versus low pitch.
Okay.
Amplitude is how big the vibration is, its intensity, like the height of a water wave or loudness for sound.
Makes sense.
And phase. Phase is a bit trickier. It's about the starting point in the cycle.
Yeah.
Imagine two kids on swings, same speed, but one starts at the top and the other starts halfway down. They're out of phase.
Okay. So where it starts in its up and down motion.
Precisely. Those are the basics we'll need.
Great. So the plan is start classical, where things make intuitive sense, then jump into quantum mechanics, where vibration is what things are.
That's the leap, yeah. Then we'll look at some cutting-edge ideas like string theory, and finally circle back to some surprisingly old philosophical thoughts on all this.
Okay, let's start classical then. The familiar world, sound, light, water waves. You said superposition is key here. How does that work?
Right. So in this everyday world, the principle of superposition reigns. It just means if you have two waves, say, traveling through the same water, the height of the water at any point is simply the sum of the heights of the individual waves.
Just add them up.
Just add them up algebraically. Crest plus crest makes a bigger crest. Crest plus trough cancels out maybe. And crucially, they pass through each other.
They don't bounce off or destroy each other.
Nope. Think about radio waves. There are tons of stations broadcasting right now. Their waves are all around us in the same space. Your radio tunes into one, ignoring the others, they coexist. Or our voices right now. They combine in the air, but they don't scramble each other permanently.
That's a good point. So this adding up, you mentioned crests adding and troughs canceling. Does that have a name?
It does. It's called interference. When waves align crest to crest or in phase, their amplitudes add. That's constructive interference. Makes things bigger, louder, brighter.
Okay.
But if they're out of phase, a crest meets a trough, their amplitudes subtract. That's destructive interference. It can make things weaker, quieter, dimmer.
Yeah.
Even cancel them out completely.
Like noise-canceling headphones. Is that the idea?
Exactly like that. They create a sound wave that's perfectly out of phase with the incoming noise, canceling it destructively.
And the pebble in a pond example fits here too, right? You drop two pebbles.
Perfect visual. You see that complex pattern where the ripples overlap? Some spots are really high waves, some are totally calm. That's constructive and destructive interference happening all over.
But the individual ripples just keep spreading out.
They do. They pass right through the interference zone like nothing happened. It's all just temporary addition and subtraction at each point in space and time.
You mentioned this applies to linear systems. What does that mean, quickly?
Yeah. Linear just means the response is proportional to the input. Double the cause, you double the effect. Most everyday waves sound at normal levels. Light behave this way. Non-linear stuff exists. It's more complex, but superposition is the rule for linear systems.
Okay, so waves add up. But how do we go the other way? How do we know what simple waves make up a complex one? Like, say, a musical note.
Now that's where the genius of Jean-Baptiste Joseph Fourier comes in. A French mathematician. He gave us Fourier analysis.
Fourier. Heard the name.
His work was revolutionary. It basically says any complex repeating waveform, no matter how weirdly shaped, can be perfectly broken down, decomposed into a sum of simple sine waves.
Not approximately, Perfectly.
Mathematically, yes. Perfectly.
Huh?
Each sine wave in the sum has its own specific frequency, amplitude, and phase. Fourier analysis gives you the recipe.
Wow, so that's the answer to the original question, in the classical world at least. The larger vibration is the complex wave, and the smaller vibrations are these sine wave components.
Precisely. The complex signal is the sum of its simpler Fourier components. It's not nesting, it's composition.
And this must be incredibly useful, practically. Engineering, maybe.
Hugely useful.
Yeah.
Imagine diagnosing a machine like a jet engine or something. You put a sensor on it, right? That measures the vibration.
Okay, you get some wiggly line on a graph over time.
Right, a complex time waveform. It tells you that it's vibrating, but not really why. So engineers use a tool called the fast Fourier transform, or FFT. It's just a fast algorithm to do Fourier analysis.
And what does the FFT do?
It takes that wiggly time signal and transforms it into a frequency spectrum. It's like a prism for vibration. Instead of seeing the overall wiggle, you see sharp peaks at specific frequencies.
Ah, so you can see the ingredient.
Exactly. A big peak at a low frequency might tell the engineer, the main rotor is unbalanced. Another peak, maybe higher up, could scream, "Warning! Bearing failure imminent!" Each problem has its own frequency signature.
So you decompose the complex noise into its simple sources. That's powerful.
It really is. It lets you pinpoint problems hidden within the overall noise.
And this connects directly to music, right? Harmonics and stuff. How does a guitar string work with this?
Perfect example. When you pluck a guitar string, it doesn't just vibrate at one frequency. It vibrates at a whole set of allowed frequencies.
Loud. Why only certain ones?
Because the string is fixed at both ends. It can only sustain vibrations that fit neatly between those ends, forming standing waves with nodes, points that don't move, and antinodes, points of maximum vibration.
Okay.
The lowest frequency that fits is called the fundamental. That's the main note you hear. But the string also vibrates at frequencies that are exact whole number multiples of the fundamental.
Multiples, like double, triple.
Exactly. If the fundamental is 100 hertz, it also vibrates at 200 hertz, 300 hertz, 400 hertz, and so on. These are the harmonics, or overtones.
So the sound I hear isn't just the fundamental.
Almost never. The rich, characteristic sound of an instrument, its timbre, comes from the specific mix, the relative loudness of its fundamental and all its overtones.
Ah, so that's why a violin sounds different from a flute playing the same note.
Precisely. A flute is almost a pure sine wave, mostly fundamental. A violin has a really rich spectrum of harmonics, giving it that complex, bright sound. A square wave, electronically generated, has only odd-numbered harmonics, giving it a sort of hollow sound. It's all about the recipe of frequencies.
So back to the choir analogy you mentioned earlier.
Yes. It's the best way to think about it classically. The rich violin tone isn't one thing with smaller things inside. It is the sum, the superposition of the fundamental vibration and all those higher frequency harmonic vibrations happening simultaneously on the same string.
Like individual singers combining for a chord.
Exactly. Coexistence and summation, not nesting.
Okay, that classical picture feels pretty solid now. But you said quantum mechanics changes things fundamentally. What's the big shift when we go quantum?
The biggest shift really is wave-particle duality. It's one of the cornerstones of quantum theory.
Right, the idea that things can be both waves and particles. Seems weird.
It is weird, but experimentally verified. An electron, for example. Sometimes it acts like a tiny billiard ball hits a detector at a single point, particle-like.
Okay.
But if you shoot a beam of electrons through two tiny slits, like you would with light waves, they create an interference pattern on the screen behind it, just like waves would.
So electrons interfere with themselves.
That's the mystery. But it shows they must have wave-like properties. The key takeaway is matter itself, fundamental particles, have an intrinsic vibrational or wave-like nature. It's not just something they do, it's part of what they are.
And that connects to energy. You mentioned energy quantization.
Directly. If a particle, like an electron, is trapped, say, in an atom, its wave nature means it can only form specific standing wave patterns, just like the guitar string.
Ah, it has to fit inside the atom.
Kind of, yeah. Only certain wavelengths and therefore certain energies are allowed. All the energies in between would destructively interfere themselves out of existence. So energy comes in discrete steps, or quanta, not continuous. Vibration dictates the allowed energy levels.
Wow. So where does quantum field theory take this? You called it our most successful theory.
QFT takes it a huge step further. It says the most fundamental things in the universe aren't particles at all. They're quantum fields.
Fields, like magnetic fields.
Yeah, sort of, but more fundamental. Imagine fields filling all of space and time. There's an electron field, a photon field for light, a Higgs field, one for each type of fundamental particle.
Okay. Fields everywhere. So where are the particles then?
This is the mind-bending part. What we think of as a particle, say an electron, is actually just the localized vibration, or more accurately, an excitation of the electron field.
Wait, the particle is a vibration of the field.
Yes, an electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Vibration isn't just something particles do anymore. Vibration is what particles are.
That changes everything. So if all electrons are just ripples in the same field, is that why all electrons are identical?
Exactly. It perfectly explains why. They're all identical excitations of the one universal electron field.
So at this deepest level, the universe is fundamentally vibrational.
That's what QFT tells us. And these vibrations, these excitations, are quantized. They come in discrete lumps.
The quanta we talked about.
Right. The smallest possible ripple, the smallest excitation of the field, corresponds to one particle. If the field is vibrating more intensely, that corresponds to multiple particles. 2 particles is like twice the minimum excitation level. It's countable.
You also mentioned quasi-particles. How do they fit in?
Quasi-particles are cool. They're like emergent phenomena in complex systems. Think of sound traveling through a crystal. It's really just atoms jiggling and passing the vibration along.
Okay.
But quantum mechanically, we can describe that collective jiggling, that sound wave, as if it were a particle itself, a phonon. A phonon isn't a fundamental particle. It's a quantized mode of vibration of the whole system of atoms. It behaves like a particle.
So it's a collective vibration acting as one unit.
Exactly. It shows how organized vibrational energy in the system can take on particle-like properties.
How does QFT actually, do the math for this? You mentioned quantum harmonic oscillators.
Yeah, mathematically, a quantum field can be thought of as an infinite collection of tiny interconnected quantum harmonic oscillators, like an infinite grid of little vibrating springs.
Okay.
And physicists use mathematical tools called creation and annihilation operators. A creation operator basically plucks one of these oscillators, adding a quantum of energy, creating a particle, a ripple.
Then annihilation.
It does the opposite. It smooths that ripple, removing a quantum of energy, destroying a particle.
So you build up states with more particles by using these operators.
Precisely. You start with the vacuum state, no particles. The field is calm, mostly, and apply creation operators to add particles, building up states with 1, 2, 3, or any number of particles. It's a very rigorous way of showing how the larger vibration, many particles, is built from the smaller ones, single particle excitations.
The vacuum state. You said mostly calm. What did you mean by that? Is the vacuum not empty?
According to QFT, absolutely not. The quantum vacuum is often described as a seething cauldron of activity.
Seriously? Empty space.
Yep. It comes from the Heisenberg uncertainty principle. You can't know both the exact value of a field and its rate of change simultaneously. So even in its lowest energy state, a quantum field is constantly undergoing tiny, random jiggles, quantum fluctuations or vacuum fluctuations.
Jiggles? What does that look like?
It's often visualized as pairs of virtual particles and antiparticles spontaneously popping into existence and then annihilating each other almost instantly. They borrow energy from the vacuum for a fleeting moment, allowed by uncertainty.
So empty space is constantly bubbling with these virtual particles.
That's the picture. The vacuum itself is vibrating. It's the ground floor, but it's not silent.
That sounds incredibly speculative. Is there any proof this actually happens?
Oh, yes. Very solid proof. The Casimir effect is one. If you place 2 metal plates extremely close together in a vacuum, they attract each other.
Why?
Because the plates restrict the kinds of virtual particles that can pop into existence between them. Fewer wavelengths fit. But outside the plates, all wavelengths are allowed. This imbalance creates a net pressure pushing the plates together.
Wow, so virtual particles are exerting real force.
They are. And another key proof is the Lamb shift. It's a tiny, tiny difference in the energy levels of hydrogen atoms that early quantum mechanics couldn't explain. But when you include the effects of these vacuum fluctuations interacting with the electron, QFT predicts the shift perfectly.
Okay, that's compelling. The vacuum isn't empty, it's dynamic and vibrating.
Undeniably so. Space-time itself is a vibrant medium.
All right, moving from the experimentally verified QFT, let's touch on the more speculative frontiers. String theory comes up a lot.
It does. String theory is, well, maybe the most famous candidate for a theory of everything, trying to unite gravity with quantum mechanics.
And its core idea is vibration again.
Absolutely central. It proposes that the fundamental constituents of reality aren't point particles or even field excitations in the QFT sense, but unimaginably tiny, one-dimensional vibrating filaments of energy string.
Tiny vibrating strings. So particles like electrons and photons are what?
They are simply different ways a string can vibrate, different resonant patterns, different modes of vibration.
Like the harmonics on a guitar string.
Exactly like that. It's the ultimate music analogy. One single type of fundamental string can appear as an electron if it vibrates one way, a photon if it vibrates another way, a quark if it vibrates yet another way. All the different particles are just different notes played on this fundamental string.
And properties like mass and charge come from the vibration.
That's the idea.
Yeah.
The energy of the vibration determines the particle's mass via E-mc/Pa. The specific pattern of vibration determines its charge and other properties. The particles we know in the standard model would be the lowest energy vibrations, the fundamental notes. Higher energy vibrations, the overtones, would be new, extremely massive particles we haven't seen yet.
It sounds incredibly elegant, one basic thing vibrating in different ways to make everything.
It is elegant, but it comes with significant theoretical baggage.
Such as?
Well, for the math to work, it generally requires extra spatial dimensions beyond the 3 we experienced, like 10 or 11 dimensions in total.
Whoa. Where are they?
The idea is they're compactified, curled up incredibly tightly, on a scale so small we can't perceive them. But the shape of these curled-up dimensions would influence how the strings can vibrate, and that would determine the fundamental constants of our universe. It also often requires a new kind of symmetry called supersymmetry.
Sounds complicated. And you said it's speculative.
Highly speculative.
Mm-hmm.
Despite decades of work, there's no direct experimental evidence for strings, extra dimensions, or supersymmetry yet. Finding such evidence is a major goal of particle physics, but it hasn't happened. So it remains a beautiful mathematical framework full of potential, but not yet confirmed physics.
Okay, so string theory offers this ultimate vibrational picture. What about fractals? You mentioned them earlier. How do they relate to this idea of larger vibrations made of smaller ones?
Fractals are fascinating because their defining feature is self-similarity. You zoom in on a fractal pattern, and you see smaller versions of the overall structure repeating. Think of a coastline, or a snowflake, or certain plant structures.
The pattern repeats at different scales.
Exactly. And that language patterns repeating across scales sounds a lot like the initial intuition about vibrations, doesn't it? A large pattern made of similar, smaller patterns.
It does, yeah.
And fractals aren't just pretty pictures. Fractal analysis is actually used to study complex systems, including some types of vibration. For example, the fractal dimension of a vibration signal from a faulty machine might indicate the type of fault. It describes the complexity and scaling of the signal.
So complex vibrations can show fractal patterns.
It can, yes. It can be an emergent property of the system's dynamics. But, and this is the crucial distinction, the fractal pattern describes the structure or the behavior that emerges.
Yeah.
It doesn't change the fundamental mechanism of how the underlying waves combine.
Ah, so the waves themselves are still adding up via superposition.
Exactly. Superposition is how the basic wave components combine, step by step. Fractals can describe the complex, self-similar dance that emerges from all those steps in certain systems. But superposition is still the choreographer, if you like.
That's a helpful distinction. Pattern versus mechanism. Okay, we've covered classical, quantum, speculative. Now, you mentioned this connects back to ancient philosophy. That seems like a big leap.
It might seem like it, but the idea that the universe is fundamentally vibrational or based on harmony is incredibly old.
Yeah.
It's not just a modern scientific concept.
Really? Like who?
Well, think of Pythagoras and his followers back in 6th century BCE Greece. We mostly know him for the theorem about triangles.
Right. A plus B equals C4.
But he was arguably more focused on numbers and music. He discovered that musical intervals that sound harmonious to us, octaves, fifth, fourths, correspond to simple whole number ratios of string lengths on an instrument like a monochord.
So simple math makes pleasing sounds.
Yes. A 2.1 ratio gives an octave, 3.2 gives a perfect fifth. It was this profound connection between abstract numbers and physical reality, experienced through sound and vibration.
And they took that further.
They did. They extrapolated it to the entire cosmos, proposing the music of the spheres. The idea was that the planets, the sun, the moon, moving in their orbits, also followed these harmonic ratios and produced a kind of celestial music.
Music of the spheres. I've heard that phrase, but we can't hear it.
Their reasoning was that it's always been there, constantly playing since we were born, so we're unaware of it, like people who live near a waterfall stop hearing the constant roar. But the core idea was a universe governed by harmony and resonance. It's really the first known attempt in the West to describe reality in terms of vibration, a philosophical ancestor to string theory, in a way.
That's amazing. Are there other ancient traditions with similar ideas?
Oh, definitely. In ancient Hindu philosophy, there's the concept of Nada Brahma. It translates roughly to sound is God, or the universe is sound.
The universe is sound.
Yes. The core principle is that everything in the manifest universe, all matter, all energy, even consciousness itself, originates from and is a manifestation of a single primordial vibration or sound.
A primordial sound creating everything.
That's the essence. The sacred syllable Om, or AUM, is often considered the closest humanly audible representation of this fundamental creative vibration. Everything that exists is seen as a particular pattern of this underlying vibrational field.
And they had practices based on this.
Yes, Nada Yoga, for instance. It involves using sound, external sounds, internal sounds, chanting, deep listening, as a way to attune one's consciousness to this fundamental vibratory nature of reality, seeking harmony and connection.
It's striking how similar some of these ideas sound to modern physics, even if the language is different.
Isn't it? Think about QFT describing particles as excitations of an underlying field. That's a modern mathematical way of saying form emerges from a formless, vibrating substrate.
Like Nada Brahma.
Very much like it. And the quantum vacuum, this ground state that's not empty but full of potential fluctuations, these constant vibrations, it really resonates with concepts of a silent potential sound from which creation emerges. Modern physics arrived here through math and experiment, but the echoes of these ancient metaphysical ideas are undeniable.
So let's try to wrap this up. We started with that simple intuition, big vibrations made of smaller ones, and the journey took us, well, quite far.
It did. We saw in classical physics that complex vibrations are sums of simpler ones, thanks to superposition and Fourier analysis, like the choir analogy voices adding up.
Right, composition, not nesting.
Then quantum mechanics took it deeper. Vibration isn't just what things do, it's what fundamental particles are quantized excitations of fields. Even empty space vibrates.
And string theory offers that ultimate, though speculative, vision. Everything as different notes played on tiny, vibrating strings.
Yeah, and at each stage, the way things compose gets more sophisticated, more fundamental.
And what's really mind-blowing is seeing how these cutting-edge scientific ideas seem to circle back and resonate with those ancient philosophical traditions like Pythagoras and Nada Brahma, who intuited a universe built on vibration and harmony millennia ago.
It suggests there's perhaps a deep, fundamental truth about the vibrational nature of reality that humans have sensed for a very long time. And science is now giving us the precise language and tools to describe it. The universe truly seems to be a grand, unfolding symphony.
So here's a final thought to leave you with. If the laws of physics are maybe just the rules of harmony for this cosmic symphony, what note are you playing in that grand orchestra?